just wanted to let you know great. So we're that's great. Welcome to week 2 of the OSU Quantum Symmetries program. One thing we're going to do this week, which is new, is we're going to give speakers the option to record their talks if we get the thing. Is it working? Where's Zach? It's working. Okay, great. So at some point, is it recording right now? Oh, we're recording right now. Okay, so we are being recorded right now. So just so you know, I still encourage you to ask all sorts of questions, no matter what you think of them. I'm planning to continue asking questions, even though they're going to be recorded and everything. And so that way we learn the best. And so yeah, without further ado, André Henriques will be giving his mini course on Segal conformal field theory, right?
Thank you. Yes. Yeah. Well. Nice little setup. I heard lots of good things from last week. Curious to see how it proceeds for myself this week. Okay, I will be talking about chiral conformal field theory. Oh, thank you. Can I have some feedback about the size of the font? Is this good for people? Is this good for recording purposes?
That you'll be able to watch later and decide.
Excellent. I'll take that as a yes. There exists a couple of different axiomatizations of the notion of chiral conformal field theory, and depending on how what kind of person you are, the field might look a bit different from, depending on which beginning point you take. So I'll just list them. Vertex operator algebras is one such axiomatization of chiral conformal field theory. There's another one that goes by the name conformal net. And this week, I will be talking about the axiomatics proposed by Graham Segal in the late 80s. And I will call that Segal CFT. Segal chiral conformal field theory. So I should say that whereas these two have been well developed, lots of people have proven lots of theorems, provided lots of constructions, know lots of things. The axiomatic proposed by Graham Segal is not very well developed. It is, well, what does it mean to be well developed? You would you need to have, for a field, for something to be well developed, you need something where, first of all, there is the ability to construct examples of these things. You have a sufficient number of examples to test whatever you're trying to test. And then the other thing is that you have a certain set of general results of the form. Take a random Segal CFT, and maybe put some assumptions. Can you prove some theorems? Both these things are lacking in this world. So there's only a very small number, extremely small number of examples that have been fully constructed. There are only so-called free theories, and there's essentially no general results available in the literature of the form a general Segal CFT, if this, then that. So yeah, so what this means is that at moments I will be just telling you things to the best of my knowledge, and sometimes I'll be like, okay, well, this I think is something that should be always true, but I don't know how to prove it, and so on. So these three approaches are thought, expected, conjectured to be mostly equivalent. Because they're both supposed to be models of the same idea, of the same notion of chiral conformal field theory. But they're actually not 100% expected to be equivalent, because there are a couple of things that are sort of built into some of these formalisms that are not built into some other formalisms. The formalism of vertex operator algebras is supposed to be completely general to capture everything. So every chiral conformal field theory should have a vertex algebra, and there's no limitations to that. The formalism of conformal nets has built into it a notion of unitarity. So not all chiral CFTs are unitary, and conformal nets can only talk about those which are. And you might speculate as whether there's ways of modifying the formalism so as to also have it be able to talk about non-unitary things. I believe that has not been done. I mean, that would be presumably interesting to do, but has not been done yet. Segal CFTs also have, I would say, something which is built in that doesn't allow to talk about everything. Rationality is a certain property. It's a certain finiteness property, which is built in. And so again, one can sort of try to see if one can push the formalism and have a variation of this that does not have rationality built in, that does not have this finiteness built in. But given that the theory is not yet developed anyways, with this assumption, there's no need to make it even more complicated. So if I'm going to formulate a conjecture saying these things are conjecturally the same, of course I need to take into account these things. They're not going to be the same because not all vertex operator algebras are unitary, and therefore we don't expect this. Okay, so let me write down a conjecture. That's just summarizing my expectation of the relation between these two things. There's an equivalence between, so here I will write VOA for this, between unitary VOAs and conformal nets. And there's an important paper by Karpikova, Higashi, Longo-Weiner that establishes this equivalence to a large extent, but it doesn't establish it in full generality. So I believe that these authors would be happy to make a conjecture saying that in full generality the equivalence should hold, but it's not a theorem yet. And why did I put unitarity? Because unitarity is built in there. Now here's a second one. There's an equivalence between rational vertex operator algebras and Segal CFTs. That one actually, I don't believe is correct. That one I believe is false as stated. There is an equivalence relation on the set of these things that one needs to mod out in order to have this correspondence. So these are up to, let me call that infinitesimal equivalence. So this is an equivalence relation on these guys. So you can have different Segal CFTs that really want to be the same, but they're just not the same for a stupid reason. And so, okay, talk about that a bit later. And then on equivalence, and the last one is going to be rational conformal nets and unitary arrow Segal CFT. And for that last one, I do not expect any need to put this. Like within each equivalence class for this equivalence relation, there should be at most one, which is unitary. It might be none, or it might be exactly one. So, okay, I'm just trying to like draw a sort of broad picture for the moment. One thing I should say, which is important, is so you might have noted that here I emphasized chiral Segal CFT. I really should be putting chiral here. And that's because there are two things that go by the name conformal field theory. If you want to be specific, they're called full conformal field theory versus chiral conformal field theory. And these things are just two different things. Those are different mathematical implementations of the same idea. They want to be the same. They're just not quite the same, but they want to be the same. Full CFTs versus chiral CFTs do not want to be the same. They want to be different things. They are different things. And so let me just, in the language of Segal CFTs, quickly tell you sort of like sketch definition of what a full CFT is and what a chiral CFT is. So a full CFT, that's the thing that I will not be spending most of my time talking about, but let me tell you what it is anyways, is defined as a functor from a cobordism category of Riemann surfaces with boundary to the category of vector spaces. So this is a, it's a symmetric monoidal functor that I just write it like that, tensor functor from a category, Borism category. These Borisms have conformal structures. They have boundary, which is one-dimensional, and bulk, which is two-dimensional. It's a tensor category, and it lands in the category of vector spaces. These vector spaces are typically going to be infinite dimensional, so you might want to elaborate exactly what you mean by vector space, but right now I'm just keeping it as a sketch. This sketch, I should say, is, as phrased, it's a bit inaccurate. And the reason it's inaccurate is that because I did not talk about any kind of anomalies or equivalently central extensions. This category here, whose so this is the usual thing. So the objects are closed one-dimensional oriented manifolds, and the morphisms are cobordisms where the bulk of the cobordism is equipped with a complex structure. And you might think, okay, well, then you roughly know what it is. Well, actually, whereas this category exists, that's not the source of this thing. You need a sort of central extension. So associated to every such morphism, there's a certain torsor that you need to, there's a torsor for the group of real numbers, and you need to plug that into the depth. It's a bit more complicated than what I'm writing. This is just a sketch. Now, a Carroll CFT and again, this is going to be a sketch, is going to be, again, a tensor functor from the very same cobordism category. But what we're going to assign to one manifold is no longer a vector space. It's going to be, depending on your preference, you might call it, it's going to be an algebra, or you might say it's going to be a concrete linear category. So if I think of associated to every one manifold, there's an algebra, then I can say, oh, I changed my mind, and instead of the algebra, I want to look at its category of representations. And then somehow I'm now in the position where I think about a category as being the image of this one manifold. But it's not just an abstract linear category. If I have an algebra, its category of representations is a category, but it also has an extra piece of data, which is the ability, given a representation, to remember the underlying vector space. That's called a concrete category. Concrete category is a linear category equipped with a faithful functor to the category of vector spaces. And so that's how I'm going to write it. It's going to be a concrete linear categories. If you want to think of this as being just assigning an algebra to every one manifold, that's an equivalent way of thinking about it. So if I have concrete linear category that consists of two data, it consists of a category, is a linear category, and it consists of a functor, which I'm going to call U for underlying vector space, that goes from C to the category of vector spaces. And again, these are some kind of infinite dimensional topological vector spaces. You might want to be specific. We might want to be specific at some point later on. Great. So that's what we assign to these guys. What do we assign to these is going to be a functor between those. What is a functor between categories? You know what that is. C to D, I have a functor. What is a functor between concrete categories? So if both of them come equipped with a forgetful functor, so I have underlying for C, and I have underlying for D. Well, one thing you could do is to say, I'm going to ask nothing. I'm going to just have a single functor. That would be not taking this piece of data seriously. And therefore, I'm going to have an extra piece of data, which is going to be a natural transformation. It goes this way, between this functor and that composite. And I'm going to call that natural transformation by the letter Z. So an object here is a pair C, U, and a morphism here is a pair F, Z. And what's important is that here there is one more condition, which is that everything is holomorphic. Whenever you can ask that something be holomorphic, you should ask that it's holomorphic. And that's a very big difference between these two sides. Here, things do not depend holomorphically on. So let me give you an example of something that. Let's look at the collection of morphisms from the empty one manifold to the empty one manifold. Okay, so now there's like no boundary. We're talking just about the closed Riemann surface. If I fix the genus, the collection of closed Riemann surfaces is an algebraic variety. It's actually an algebraic stack, but whatever. It's a thing that has a complex structure. And when I talk about a function on it, it makes sense to ask, is that function holomorphic? So if I have one of these full CFTs, what am I going to assign to the empty one manifold? I'm going to assign the trivial vector space, i.e. the complex numbers, like a one-dimensional vector space. And then, so this is really a bit of an aside, so I'll just do it here. So I have here complex manifold, one of those, and I have here the trivial manifold, which is empty, and then my functor is going to assign to this the complex numbers, assigns here the complex number, and assigns here a thing which is just a number. Let's call this thing E for elliptic curve, and this number I'm going to call it Z of E. That's what physicists call the partition function. You can ask, how is Z of E a function of E? The set of all possible E's is the moduli space of elliptic curves. It's an algebraic variety. Is this something that's going to be a holomorphic function on that? Is that something that we want to be holomorphic? And in this setup, in the context of full CFTs, the answer is no. We do not want that to be holomorphic. This is typically, in all interesting examples, it is going to be a real analytic function, which is not complex analytic. So no for full CFTs. Okay, so
was there some compatibility with braiding for full version? But
sorry?
Did you say the full CFT has compatibility with braiding?
Compatibility with braiding. This is a symmetric monoidal functor.
Yeah, but so the chiral CFT is also, do you also want to do?
This is also a symmetric monoidal functor.
Okay, so you want your concrete linear category to be symmetric monoidal category with embedded vector spaces.
The collection of all concrete linear categories is something which is symmetric monoidal.
Okay, I see. So it's going to be category of categories.
That's right. So this is really a thing whose objects are, so that's an object of the collection of all concrete linear categories, and that's a morphism. So a Segal CFT is going to assign to every one manifold one of those, namely a pair, and to every morphism one of those, namely a pair. And then there's some conditions of holomorphicity that I need to explain. So there's a number of little preliminaries that one needs to set up in order to be able to fully describe this notion here. I'll do some of them now and some of them maybe tomorrow. One of these things that one needs to say exactly what it means is what is a complex cobordism between one-dimensional manifolds. I don't need to explain what a one-dimensional manifold is. That's a smooth, one-dimensional oriented, compact manifold. You know what that is. But one of these, well, it's a manifold with boundary, and it has a complex structure. How does one compose exactly these things? Might be something that, well, I mean, you might think, oh, yeah, I know how to do it. But then if you actually think about it, you might think, oh, I don't know how to do it. Because if you look at where this complex structure is defined, it's defined only on the interior, not all the way to the boundary. So if you perform a gluing, then there is a locus where the complex structure is not defined, and you need to do something. And it's just a tiny bit fiddly to set this up. And it depends on some theorems that it does work. So let me tell you how. Let me tell you what a complex cobordism is, what one of these is. I'm going to take the approach of ringed spaces. So everything is going to be a space with a sheaf of rings. It's sort of, so if I talk about, well, I mean, if you talk about like one of these, it's sort of standard in algebraic geometry to think about the space with a sheaf of rings, except I'm going to be thinking about not the sheaf of algebraic functions, but rather the sheaf of analytic functions. So to every open, you have the notion of holomorphic functions. So I'm going to be talking about some sort of sheaf of analytic functions on these guys. So what is the local model of this? The local model is going to be, well, either I'm around the point in the middle, in which case the local model is the complex plane. And I mean, around here, like I locally look like a piece of the complex plane, equipped with its sheaf of analytic functions. Or I'm at a point here, and then the local model is going to be the upper half plane, standardly denoted H. And now I need to give you a sheaf of functions on that. And the sheaf of functions that I'm going to take is the functions which are that are C infinity all the way to the boundary and analytic in the interior. Namely, away from the boundary, you want to be analytic, and as you go all the way to the boundary, you want it to be C infinity. What does it mean for a function to be C infinity all the way to the boundary? Well, you just take your usual notion of C infinity. You just remember from like first or second year of undergrad, and you learned about what it means for it to be C infinity, and then you apply it there to this context of manifolds with boundaries. And sometimes you will be taking some limits to define a derivative, like you want the limit to exist, and you're not able to go on the other side because there's just no points in your manifold on the other side. Well, then you just take the limit just on one side and require that it exists and go on like that. So that turns out to be equivalent to being the restriction of a C infinity function defined on some actual open of the complex plane. That's a somewhat non-trivial statement, what I just said, known as Borel's lemma, and it's just two equivalent ways of talking about C infinity functions on a manifold with boundary. Great. So now I told you what one of these is. It's a thing that looks like that, it's equipped to the sheaf of rings, and locally it looks either like a piece of that or like a piece of that. The tricky thing is how you glue these things. If I take That's called conformal welding, also known as gluing of Riemann surfaces with boundary. Suppose I have two complex cobordisms that want to be composable. Namely, there's a chosen map phi from this boundary. Let's call this sigma 1. Let's call this sigma 2. Let's call this the incoming boundary, and let's call that the outgoing boundary. I will be using the color code that blue is outgoing and red is incoming. And for some reason, I'm always going to put the incoming on one side and the outgoing on the other side. And phi is an isomorphism. It's a diffeomorphism from the incoming boundary of sigma 1 to the outgoing boundary of sigma 2. Then you want to be able to form a new thing where what used to be that curve is now a single curve, which is in the middle of this thing. And I'm going to perform, so this is usually, so suppose these were just topological manifolds. How would I perform this? I would say, take the disjoint union and take an equivalence relation that identifies a point here with phi of that point over there, and then form the quotient topological space. That's called the pushout. I have a diagram that has this space, that space, and then an abstract little circle here, mapping there, and you form the pushout diagram, and the resulting topological space is this thing here. Now, I claim that if you perform the pushout in the category of ringed spaces, so what does it mean to take the pushout in the category of ringed spaces? It means I take the pushout in the category of topological spaces, and then I'm going to equip it with a certain sheaf of rings that's going to be determined in terms of the sheaves, in terms of the things that I have here. So if I have an open here, well, either it lands entirely here, in which case I know what it means to be a function, or it lands entirely on the other side, in which case I do know, or it crosses over that line, in which case the preimage is something that has a bit here and a bit there. And then a function on this is going to be, by definition, or an element of my structure sheaf here is going to be, by definition, a pair consisting of an element here, a function here, and a function there, with a property that they agree on the place where it makes sense for them to agree. And now, here's a somewhat surprising fact, which is, I mean, there's a whole theory called conformal welding. I'm sort of summarizing it. If you perform the pushout in the category of ring spaces, you get, again, something which is one of those. Again, it is locally what you want.
So that means so circle has the canonical ring space structure.
Sorry?
So you restrict these holomorphic functions from sigma to the boundary circle, and the two restrictions coming from sigma 1 and sigma 2 have to agree, right?
Yes.
And is it part of the assumption? Or
yeah, so the statement is that a function on this let me write it down as, I think it's going to be notationally a little bit heavy if I keep track of these little opens. So let me just write it down for globally defined holomorphic functions. So a function on, well, actually, there's no need to. So let's call this thing U. It's an open. Let's call this thing U1. It's the preimage of U under the inclusion of sigma 1. Let's call this thing U2. It's the inclusion preimage of U under the inclusion of sigma 2. So a function on U is in my structure sheaf. So this is now a definition of the structure sheaf of sigma 1 glued along phi with sigma 2. If function f, let's say, if f restricted to sigma 1 belongs to O, I guess a sheaf needs to be evaluated. So it's a sheaf on U. If this belongs to O sub sigma 1 of U1, and F restricted to sigma 2 belongs in O sub sigma 2 of U2. So this is a definition of a sheaf on this space. And now the non-trivial claim is that this new ringed space that I've defined, namely topological space with sheaf of rings, is one which is locally isomorphic to this, around one of those points where you a priori have no expectation that it should be, because I've done something a bit weird, right? This is a thing that has in it, like the word C infinity, so there's no analyticity condition at the boundary. The diffeomorphism here is only C infinity. It's not required to be analytic. And therefore, there's a sort of automatic from C infinity to analytic that's happening that's built into that, and that's a bit surprising.
So basically, you have a smooth function on a boundary of some open domain, and you can extend it to analytic function.
Yeah, so this line here is going to be a line which is not necessarily embedded in a real analytic way. It's going to be only embedded in a C infinity way. And therefore, the restriction to it is going to only be C infinity, because it doesn't make sense to ask that the restriction be real analytic, given that this one manifold does not admit a real analytic structure. It's only, so anyways, this is not really what I want to focus on. I'm just telling you that this is part of the things that you need to fight with a little bit before you can even start doing things. Really what you want to know is you want to sort of put yourself in the position where you're like, oh, I know how this works. I'm going to do something with it. But I'm telling you, well, you don't know what it works. It's like it's complicated. Actually, it's going to be even more complicated because this doesn't have identities. You don't have the ability to just have the red curve and the blue curve just touch each other, and you very much want to allow that. Well, you might say you like adding identities is just a formal thing. You just add identities, and then you have a thing with identities. But really what you want to be adding is the possibility to have the red and the blue touch along some part and then split, and then touch again, and then split if they want. So if you want to also account for that possibility, then So then a typical thing that you might be forced to consider as an example of a morphism is something that has this thing here. That is also something I want to allow. And then suddenly you need to think about what is the local model for that, because this is no longer isomorphic to either this or that locally. There's a funny point here where things are totally different. And then what you end up having to say is that the local model is going to be given by, well, suppose I have the graph of two functions. One is the blue is the one graph, and the red is some other graph. And then you ask that you look at the function defined on like functions which are the restriction of a smooth function in neighborhoods with the property that on the interior they're analytic, and on the boundaries, namely restricted to the blue curve and restricted to the red curve, they're seen. And then these things are now the things that you look at, and then there's an elaboration of this that tells you that if you perform this push out and ring spaces for those guys, then it again works. Yes?
What's the problem with like cylinders?
There's no problem with cylinders. Cylinders are also allowed.
Can you interpret some of them as like the identity?
Well, they're not the identity, because we're looking at things with complex structure, and they're just not the identity because the complex structure is there.
So are the morphisms, these morphisms, considered after some equivalence relation? Like what is the equivalence relation on coordinate with complex structure?
So if you fix the blue manifold and the red manifold, you can look at the collection of all complex cobordisms that go from one to the other. That's going to be a groupoid where you can have interesting automorphisms. Actually, they only happen in the special cases when you have closed components. Like this, for example, morphism has interesting automorphisms because the elliptic curve has automorphisms. And so really, this is a 2 category. Correspondingly, that is also a 2 category, because if you think about it, well, we have objects, morphisms, but morphisms are some kind of functors, and then you also have the natural transformations. So we're talking here about a symmetrical non-functor between a certain symmetrical model 2 category and another symmetrical model 2 category.
So is that really what you want, or is this a truncation?
No, that's what I want.
Oh.
I didn't say it all from the beginning, but that's really what I want. So, okay. So now let me maybe unpack this definition, because it's good to have it in packaged format where you just have it like in a very succinct form, but then maybe in order to be able to say what this last condition is, I need to unpack it. It's like just not possible to say it effectively without unpacking. Okay, so great. So what is one of these things? First of all, for every one manifold S, I'm going to have one of these concrete linear categories. I have a category C of S. It's a linear category. And then I also have this forgetful functor U from C of S to vector spaces. And I think of those as being 2 different pieces of data that are both associated to S. If I have sigma is going to be my generic letter for this is so this is S1, S2, and here I have sigma. So suppose sigma goes from S1 to S2, as in this picture here. Then the first thing that I have is a functor this way. F from C of S1 to C of S2. Then there's this piece of data here, which is maybe a little bit unfamiliar, but let's write it down. It's going to be, so this depends on sigma. Let's write it like that. Now I have a Z sub sigma. So what is a natural transformation? It is for every object here, a map. Now it's going to be a map in this category, so it's going to be a linear map between this and that. So it's a map from the underlying vector space of some object lambda. So I have now some lambda in the category associated to S1. And it goes to, let me just push this a bit more, to the underlying vector space of F sigma of lambda. And if you think of this as being, there's a certain algebra associated to S, and that's a category of representations. Here I have a functor between these categories of representations. This functor, this linear map here is not a map of representations. It's just a map of underlying vector spaces, because it happens down here. And what's a typical way that you would get such a map? It's if you have an algebra associated to this, an algebra associated to that, a bimodule associated to this. The bimodule is the thing that buys you this map here. Tensoring with the bimodule is a way of producing functors. But then you need an element in your bimodule. And the element in the bimodule is what produces this thing here. Because if I have an element in the module, that's an element in here, then I can get an element in the module tensor bimodule only if I have an element of the bimodule, and then I can do that. So you should think of it as being algebras and pointed bimodules. That's one equivalent way of thinking about this. Anyways, I like this sort of more abstract, more categorical way of talking about it, which is pretty much equivalent. So now let me tell you about this. What does it mean that things are holomorphic? What I want to say is that this linear map depends holomorphically on the choice of sigma. There's a couple of issues there. First of all, I need to tell you how the collection of all such sigmas for fixed S1 and S2 is a holomorphic thing. So the collection of all complex cobordisms between fixed one manifolds is supposed to be some infinite dimensional complex manifold. Well, so that's a tricky type of statement to try to understand. And also, it's not really a manifold. It's more like a manifold with boundary, because we have, right, these cylinders are allowed to have a certain length, and then the length is allowed to go to 0, but then it's not allowed to become negative. So I'll just leave it like that for the moment. This is, James is laughing.
Sorry, so even if you fix topology type of sigma, the dimension of complex structures to infinite dimension?
Yes. So the very simplest case, where you already have something which is infinite dimensional, is when S1 is a single circle, S2 is empty, sigma is a disk. I'm looking at the moduli space of all possible disks that I can put that bound S1. And the thing is that you fix S1, you fix the circle, and then there's like really lots and lots of different ways of putting a disk there. So a disk is the same thing as a essentially as a choice of which C infinity functions are going to extend to holomorphic functions on the disk, and there's just like many possibilities. Let me go on because I want to just finish what I'm saying related to this condition. In order to be able to say Z sigma depends holomorphically on sigma, first of all, I need to know that the moduli space of all sigmas is holomorphic, but OK, I told you that. But the other thing that we have to have is we need to have these linear maps mapping between the same spaces. It can't be like I'm having a collection of maps, but they're all like mapping into different targets. So OK, this doesn't depend on sigma, but this does depend on sigma. And therefore, we need to do something about it. And so we need to somehow first say that F sigma depends topologically on sigma. F sigma doesn't care about the complex structure, only cares about the genus. And then once you know that, and this is the thing that doesn't depend on sigma as you vary sigma locally, and then it's the same source and target, then you can talk about this depending. So to make sense of F sigma depending topologically on sigma, so then you do the usual thing that you do in category theory. Whenever you want to say those two things are the same, if these things are numbers, you just say they're the same. But if they're elements of some category, you don't say they're the same. You add some isomorphisms between them. So we're going to add some more isomorphisms that tell me that if I change the complex structure without changing the genus, the corresponding F sigmas are the same. So F sigmas depend so this is going to depend topologically on sigma. And that's going to depend holomorphically on sigma. So here's the way you say it. In order to make things depend topologically, it's enough to say that annuli behave like identities. Things like that, or things that have, you want those to not do anything. You want the corresponding functor. If this is sigma, I want to say F sigma is trivial. So then, like you say, if A is an annulus, so I'm going to use the letter A when sigma has the property that its incoming boundary is a circle, its outgoing boundary is a circle, and sigma is itself homotopy equivalent to a circle. And I call that an annulus. What's an annulus? Because if I draw one which is a bit more round, then it looks like an annulus. That's an annulus. So if A is an annulus, then I want a trivialization of F sub A. And then once you have that, then you can say, then this doesn't matter. And then you say, again, if A is an annulus, then I want Z sub A depends holomorphically on A, which now makes sense because that's just U of lambda, that's just U of lambda, and so it's the same vector space, and it's just a collection of maps. So this is sending A to something that is always the same, and it makes sense to be holomorphic. I lied a little bit here. There is a thing called central charge in conformal field theory. The central charge it's an anomaly. It's a thing that life would be easier if it wasn't there. If I give you if you give me an analysis, this trivialization only exists up to an ambiguity, up to a scalar that you just don't have a chosen trivialization. You have just a C star worth of trivializations. And really what you have is that you have the collection of all analytes with fixed, sorry, this is in the context when S1 equals S2. If S1 equals S2, we're talking about functors from a category to itself, and then it makes sense to trivialize something. It makes sense to say, I want this functor to be the same thing as the identity functor. So the collection of analytes with incoming and outgoing boundary parameterized by this fixed one manifold S1 admits a certain central extension, and it's really an analysis plus a lift to that central extension that produces a trivialization. So if I have an analysis plus a certain lift, lift A tilde, then the trivialization depends on A tilde. And different lifts will have the trivialization that differ by a scalar. But that is something I will be talking about tomorrow, all these anomalies. Great, my time is up.
Any questions for Andre?
Sorry, so at the end, so the choice of central charge didn't depend on, doesn't depend on the sort of holomorphicity of TA, or what's the charge? So you don't want to change this one.
I don't want to what?
You have to choose a tweet, but does it affect the last condition about?
Oh, this condition here. Yes. So that thing is a thing that you can only talk about once you're able to trivialize this. You're able to trivialize it only once you have the trivialization.
Yeah.
So this is going to depend holomorphically on A tilde now.
But does it really depend on the choice of a twiddle? Or
Yes, it does.
You said that the different choices are scalar multiple.
They're scalar multiple of each other. So here, let me just so we have lambda in C of S1. I have U of lambda. Then I have Z that depends only on the analysis. So that's OK. It goes to U of F of analysis of lambda. And then I have a certain trivialization that allows me to go back to U sub, and here I put the identity functor of lambda. And that trivialization depends on A tilde. So if I call that trivialization T sub A tilde, that is now T sub A tilde, or rather it's U of T sub A tilde. So the map which I want to be holomorphic is the map that sends A tilde to this composite. That map is a map which is required to be holomorphic. And it's a map not from the collection of analytes with boundary parameterized by S1, but from the collection, from the central extension of that group. So this map is holomorphic.
if we ignore this the anomaly issue, is there a sense in which we can think of this as some sort of as this conformal field theory as being somehow relative to a topological field theory? And that if you extract this topological field theory, that you get there as a sort of transformation into this topological field theory.
So we can focus on just the part which is topological. So the part which I have boxed in purple, that's, you can call that topological. It's not completely topological because of, I mean, sigma still has a complex structure, and we still have explicitly this stuff happening, but this, like the stuff that feels topological. This is something which I expect is equivalent to what is known in the literature as a modular functor. I don't know for sure. I haven't proven that this is the same thing as a modular functor. I just strongly expect that it is. And then on top of the modular functor, you have some extra data, this, and that condition. And that's what you need to upgrade your modular functor to a chiral conformal field theory.
You mentioned conformal welding as a way of doing Riemann surfaces. Does it provide this upside over if you're using something like collars instead? Would you get a different answer?
So if you use colors, namely if I require that the Riemann surface extends tiny bits to the right and to the left there, and they also require that this curve is, say, embedded in a real analytic way, I don't expect that to produce huge changes in the theory, but it is convenient, specifically if you want to talk about the translation between chiral Segal CFTs and conformal nets, to be able to draw pictures like that, because for a conformal net, one cares about operators that are supported on some interval, and then you want to be able to like produce examples of such things by drawing pictures like that. And then it's really important to have a thing that is like really identical on one side and not identical on the other side. And it's just not possible to have this behavior when things are real analytic, as you well know.
Does it have to be real analytic?
Sorry?
Is there any reason the curve has to be real analytic?
Any reason why the curve has to be real analytic? You're saying one can do that in the presence of colors. There's other problems. So here's the other problems. So you want very much the circle to have diff S1 as its automorphisms. That sounds like a tautology, that the automorphisms of the circle should be diff S1. This group is an important group in conformal field theory. It appears a lot. If you put colors, if my circle is suddenly not a circle, but a circle with a little bit more. Equivalently, if I'm talking about it as a ringed space equipped with the ring of functions, not of C infinity functions, but the ring of real analytic functions, then you suddenly have way fewer automorphisms. You only have the real analytic diffeomorphisms. But worse, the groupoid of all circles becomes very disconnected. specifically, if you allow things that are not real analytic, I can draw a circle and I can draw another circle. And they're just not isomorphic, because here I chose the embedding to be real analytic, and here I chose it to not be real analytic. And so you suddenly have many, many, many circles that want to be the same one manifold, but they're not. And that's a thing that's not good. So I think that ultimately, at the end of the day, it doesn't really matter, and it's a matter of just navigating through all kinds of little choices to make your life easier. And I'm just pointing out to things that one would have to deal with in case one took some different choice, made some different choices at the beginning.
Okay, let's thank André again. Let's start at 1:15.
This and that. Yeah, the collection of all these.